In this lab, our goal is to be able to identify some substances as either ionic or covalent, and furthermore, to identify what the substance is, what we call it, what it is chemically, based on some experimental tests we can do to it. What we're going to see is that ionic compounds and covalent compounds have some characteristics that you can really test for well in the lab. Specifically, we're going to be mostly looking for things that ionic compounds do that covalent compounds don't. So we're going to be looking at substances that all look very similar. They all are a white, either crystalline powder or pellets or something like that. So they can't just be kind of judged by sight on which one is which. And we'll be kind of giving them a battery of tests to see if we can figure out which one's which. So just to kind of review what ionic bonding is like to give us an idea of why we're going to get these properties. Ionic bonding happens by doing a little give and take of electrons. So we end up with oppositely charged ions. We call the positive ones cations, the negative ones anions. And so we end up with repeating ions attracted to each other over and over and over again. Positive, negative, cation, anion. So once you do a little give and take, they become charged, they attract to each other, and they stick to each other to become an ionic compound. And the attraction that holds them together is called the ionic bond. Okay. Overall, we end up with an electrically neutral substance. So all those charges should cancel out. All the positives have a negative to go with them. Okay. And in the process of making something ionically bond together and making a compound, we need a little bit of a push to get our electrons moving from one substance or from one element to another to get the bond to happen. But once the bond is formed, that's more stable. We get things to an octet through this kind of mutual benefit of either gaining or losing electrons. And then attraction pulls things closer together, and it kind of follows the physics of that attraction. So overall, once we get that transfer of electrons, we get things with a stable electron configuration. We get them to an octet or an otherwise noble gas configuration. And then the attraction pulls those atoms together. We end up with overall a more stable substance. So we end up releasing energy typically as we put together ionic compounds. Okay, that would mean that we would have to put energy in to break them apart, to separate ions of opposite charges. Okay, what we end up with is what we call a crystal lattice. It's like a repeating set of ionic bonding where our formula for the ionic compound, like NaCl or MgCl2, tells us the ratio of cations to anions for that substance, for that compound. So instead of just having, one Mg and two Cls, and then that's the substance, it's usually a whole bunch of Mg ions and Cl ions, but they happen to be in the ratio of one magnesium ion for every two chlorine ions, or rather chloride ions. Okay? Because of this repeating crystal lattice and the attractions between charges, we end up with something that is hard to break chemically. Sure, you can beat it against the desk or hit it with a hammer and shatter it that way, but down to the chemical level, separating those ions chemically and breaking that ionic bond, that ionic attraction, is very hard. It takes a lot of energy to do so because we essentially have to make things more unstable if we're fighting against that ionic bond. So what does this lead us to if we have these strong ionic bonds that make ionic compounds and they repeat over and over and over again? Well, we end up with high melting points and high boiling points for ionic compounds because of those strong ionic bonds. After all, in order for something to melt, we need particles to be able to move somewhat freely from each other. They need to be able to move past each other and roll around and rotate and things like that. As a solid, ionic compounds are fixed in place. The particles can vibrate next to each other, but that's about it. In order to get something to melt, then we essentially have to break the ionic bonds. We have to sever those connections that hold the ions so tightly together. It's going to take a lot of energy to do that, and therefore a high temperature. Okay? So if we really crank up the temperature, we can get those ions to shake themselves out of place and get them to kind of dislodge from that repeating pattern, that repeating crystal lattice, and get them to move around like that. But it is going to take a very high temperature, sometimes up in the thousands of degrees Celsius. Okay? Even further so, if we want to boil that ionic compound into a gas, it's going to take even more. It's going to take even a higher temperature, because it's already hard enough to get them to get away from each other, but as a liquid, they're still kind of rolling around and attracting to each other to an extent. To get them to be a gas, we have to totally free them from that. So it's going to take a lot of energy to keep them from going and attracting back to stuff and sticking together as a liquid or solid. Okay? So typically, things with high melting points and boiling points are a good indication that we might be dealing with an ionic compound. Something else is that they can conduct electricity when they're dissolved in water. If you take a piece of, rock salt or something like that, an ionic compound, magnesium sulfate, and put a conductivity tester to it, you're not going to get any, charge moving across it. You can't conduct electricity through a solid ionic compound. But what you can do is break up those ions in water. Ionic compounds typically dissolve very well in water. There are a couple exceptions to this that we'll talk about here at the bottom of this slide. But typically, ionic compounds break up pretty well in water, which might seem a little weird at first, since we apparently need a very, very high temperature to break ionic bonds. If they're going to dissolve in water and result in ions floating around like Na plus and Cl minus, that's breaking an ionic bond too. But here's the difference. In water, we end up with these water molecules kind of surrounding the cations and anions in a way that is actually somewhat stable. So instead of just trying to rip the ions apart and keep them apart, we put them into an alternative situation that is maybe not as stable, but it's not so bad comparatively. Okay, it's a good alternate for what the ionic bond is. So we can get these water molecules to kind of wedge themselves in between the ions and kind of wiggle their way in and kind of carry away cations and anions. They basically surround them in these little shells. So you have these little water molecules kind of surrounding an ion and taking it with them and carrying it away from the crystal lattice. So if we can get those ions to separate from each other and then move through the water, that's electricity. Typically, we think of electricity as moving electrons, but it can be really any kind of charge, positive or negative. So we can get ionic compounds to conduct electricity by breaking the ions apart and getting them apart from each other and getting them to freely float in water. Okay. Something else about ionic compounds is that they tend to be hard. They tend to be brittle because of those, again, strong ionic bonds in that repeating pattern. Okay. They also break on what we call cleavage planes. If you ever see like a very, very, very close-up, like microscope picture of a salt crystal, you'll see it has these very nice kind of ridges that are very like straight at 90-degree angles. Okay, even when you like chip it on the edge, you'll see that it breaks down to, at some level, some very, very tiny structure, 90-degree angles. You have very flat surfaces where it breaks along. It doesn't just like shear at a diagonal or something like that. There are other ionic compounds that do shear at a very nice diagonal. Like I encourage you to look up pictures of calcium carbonate. It's a good one. Or fluorite. Some crystals grow just in these nice kind of flat planes, like pyrite. So we can get these repeating structures to actually show themselves at the microscopic level, what we can see with our eyes, because they repeat so well. So this kind of repeating structure of cation, anion can actually show itself to crystals that you can see with your eyes. Okay, even when it's not exactly a 1-to-1 ratio, it's maybe 1 cation to 2 anions, or 3 anions to 2 cations, or something like that. We can still get a nice repeating structure over and over that you can actually see. So that can be a good hint that you're working with an ionic compound too, and not a covalent compound. Okay, the structure that we do see depends on that ratio. So depending on how this thing stacks up, you're going to get a different kind of shape of your crystal. So like NaCl is pretty straightforward, and then it has to repeat Na plus and then Cl minus and then Na plus and Cl minus, which is where we get this very nice and neat kind of cubic structure. But something like calcium carbonate is a lot more complicated in how those atoms sit next to each other. So we end up with this curious kind of slanted, kind of like a rhombohedron or something like that. Okay. Uh, another kind of property of an ionic compound is that we can form what we call precipitates. Precipitates are a solid that show up when something is dissolved in water, or we try to dissolve stuff in water. So you can kind of think of it like this. When we dissolve ionic compounds in water, the ions get free of each other. The water kind of carries them off. Okay. And that's because dissolving them in water is a stable alternative to being together in the ionic crystal. We end up kind of giving them, it's not the ionic attraction that they're used to, but we can surround them with so many water molecules that it's fine. It's acceptable. Okay. Now, once those ions are floating around, sometimes there are ions that can meet each other and attract so strongly that even the water can't kind of keep them apart. It's not a stable enough alternative for those ions. They'd rather come back together as a compound. Okay, when that happens, we form what we call a precipitate, which is basically a substance that does not dissolve. It is insoluble. So rather than dissolving and breaking down, it forms back into a solid thing that's going to settle out at the bottom of your test tube or flask or beaker or whatever you're using. Okay, so we end up basically with a chemical reaction that forms a new ionic compound out of existing ions floating around. So sometimes we can test for ions that are in these compounds by dissolving them in water first, and then throwing in other ionic compounds that are already dissolved to see what reactions and precipitates we can make. So for instance, a lot of bigger, heavier metals in ionic compounds tend to form precipitates, like lead or silver. So if I suspect that my ionic compound has lead in it, I might try throwing in some other substances that, like maybe potassium iodide or potassium nitrate or something like that, to see if I can get some ions to kind of collect, maybe like potassium sulfate, to see if I can get some ions to meet each other and form a precipitate. So if I can say, ooh, I added this in and then it precipitated and I get a solid instead, what combinations of ions can make a precipitate like this? And I can kind of piece out what was in the original ionic compound I was using. Okay, so how does this work for us? Well, we can use these to kind of be, again, characteristic kind of test results to show us whether we're dealing with an ionic compound or a covalent compound. So for instance, when we are dissolving ionic compounds in water, we are breaking up some ionic bonds, and depending on how kind of suitable that kind of surrounding of the ion is for the water molecules involved and the ions involved, kind of breaking them apart, we might have some heat absorbed or released by that process. So if things become a little bit more stable to dissolve them in water, and it's like, ooh, this is actually a little bit better than the attraction from the bonding, then that dissolving process can release heat. We have extra energy that is kind of let out. Okay, or if it's still more suitable for those ions to be with each other instead of the water, but the water still grabs them and pulls them away anyway, it might end up absorbing some heat. And so therefore your temperature is going to go down. So feeling a temperature change can kind of indicate what's going on, and be like, ooh, there are ionic bonds that are breaking, and whether it is more stable or less stable tells us whether the temperature goes up or down. Okay. Because of that breaking into ions part, we can also conduct electricity through water. So if you can put a conductivity tester in your solution, your dissolved ionic compound in water, and you can get a little light bulb to show up, to turn on, to light up, then that's a good sign that electricity is moving, which means you must have charges in your water. Now, an important thing is to use distilled water to start with, because tap water does already have some ions floating around in it. So you might get a kind of a false positive result because you already had some ions in there. It doesn't mean that the stuff you dissolved had ions too. All right. When ionic compounds react in a solution to form a precipitate, we can use that to figure out what was originally in the ionic compound. Okay. Those precipitates that form are too strong ionically. Their attractions between the ions are too strong to break up with the water. And just for funsies, these can actually have some really cool colors and looks, and so they're just kind of neat to see and to test for. Okay, finally, and this is one I didn't bring up before, we can also test for acids and bases if we know kind of what we're looking for. So let's say like we're looking for we're trying to identify which substance is an acid. Maybe it's like adipic acid or salicylic acid or something like that. Well, if I can dissolve it and test it with a pH strip, that'll tell me how acidic or basic it is. And so if it lands on kind of neutral, it's not really acidic or basic, I can probably scratch it out as like, ooh, this is probably not adipic acid or salicylic acid or whatever. Okay. Or if it's on one side or the other, I might give it like a little bit of a thought, like, ooh, this is coming out with a pH lower than 7. So it's, the strip is coming out like a reddish color or an orangish color. I'm dealing with an acid here. So which acid could this be? Is it ionic or is it covalent? A lot of acids are covalent, but they might still break up in water. It gets a little confusing. Okay, a lot of bases are ionic. So we have a lot of bases that are ionic, some acids that are ionic, but mostly kind of they kind of lean on the covalent side. But we can kind of easily knock out like, ooh, I found the base or I found the acid by testing with a pH strip and seeing, stuff like that. Okay, in general, covalent compounds are not going to do most of the exciting stuff that we're looking for. So since covalent molecules exist in little neutral bundles of shared electrons, there's no ions there to liberate. So whether I try and break a covalent bond or not, that's not going to do anything for, conducting electricity in water and stuff like that. Okay. As a result, there's also not really anything for the water to get in between and kind of pull out. Water is really good at breaking up ionic compounds to dissolve them because of those charges. The water molecules have a little bit of an attraction to those ions and can group up around them. Water doesn't really have a reason to get in between atoms that are covalently bonded. So we don't see them break up. We don't break any bonds when we put covalent compounds in water. Okay, this isn't mentioned here, but covalent compounds also tend to have lower melting points and boiling points. We're not testing that in this lab, but because your covalent molecules are separate from each other, they're a little bit more loosely attached to each other. There are still attractions from one molecule to another, but they aren't bonds. Okay, and even then, a covalent bond would be less strong than an ionic bond. Okay, but when it comes down to it, whatever our covalent substance is made up of a bunch of separate molecules that are only weakly attracted to each other. It's not going to take much energy to loosen them apart from each other, get them moving and grooving, and therefore melt them, or get them to go a little bit farther and boil them into a gas. Because we don't have to break a bond to do that, to get those molecules moving apart from each other. We just have to kind of fend off the weaker attractions that hold them near each other. Okay, covalent compounds will also not form precipitates since they're not breaking apart into ions. Again, there are some compounds that you might consider covalent that might be acidic, but for this lab, at least, we're going to focus on ionic stuff that changes our pH. Stuff that is going to break up into ions and then can be kind of detected with a conductivity tester and also change a pH strip. So hopefully this kind of list of different things we can try on in a compound will help you kind of rule out which compound is which and figure out what the identities of each substance is.